Okay, so this video is going to be a little introduction to organic chemistry. We're going to talk about the alkanes, which is the family of organic compounds, and we'll do a very brief introduction to isomers. So organic chemistry is the chemistry of carbon compounds, and there are more compounds based on carbon than all other types of compounds combined, and that's why it's its own branch of chemistry. Carbon has 4 valence electrons, and so normally forms 4 covalent bonds, and it's able to form these really extensive, complicated chains and rings with itself, which is why there's so much variety. Luckily, though, actually drawing the structures, the elements tend to obey the octet rule, and so they're pretty simple to draw if you remember the simple rules. Carbon's going to form 4 bonds, usually forming the backbone of the molecules. Hydrogen, only 1 bond, always sort of filling out the outsides of molecules, never between 2 atoms. Oxygen forms 2 bonds, so either a double bond to 1 atom or single bonds to 2 different atoms. And nitrogen, 3 bonds, so that could be single, double, or triple bonds, some combination of those. There are some examples where oxygen and nitrogen make up part of the chain of the molecule rather than sticking off to the side, but for most of what you'll see in IB chemistry, they tend to stick off the chain of carbon atoms. So organic chemistry is going to introduce a couple of slightly new types of formulas for us. We've previously looked at empirical formulas and molecular formulas. That's sort of what we're used to. In organic chemistry, you're often going to be asked to draw or look at full structural formulas. So these are very similar to Lewis structures, except that they don't need to show lone pairs or non-bonding pairs of electrons. If you look at this structure for butanone, it doesn't have the 2 lone pairs on the oxygen. So usually you leave out the electron pairs. They're sort of assumed. You also tend not to show the correct VSEPR geometry. Usually carbon chains are drawn with all the bonds sticking out sort of at 90-degree angles, just to make it a bit easier to interpret on the page. So they're perhaps a bit less accurate than those structures, but as organic molecules get so complicated, it helps sort of streamline the process of drawing them and makes it a bit less messy when you draw them. So it's basically a Lewis structure, but you get to leave out a couple of the details to make it simpler. But something that's new, you may have seen it on some exam questions, but it's really going to be new for us at this point, is something called a condensed structural formula. So it shows all the atoms, and some of the bonds might actually be shown, but instead of just clumping everything together, like for example, pentane, its molecular formula is C5, and if you count up all the H's, it's H12. But just telling me that pentane's formula is C5H12 is actually not very helpful, because there's more than one way that you can put 5 carbons and 12 hydrogens together. So, and we'll get to that in a minute, but the point is, if I can write it in a similar way to a molecular formula, but give you a bit more information about how the different atoms and groups go together, that's a lot more useful. So a condensed structural formula is a more useful molecular formula. So if you look at the structure of pentane above, and you look down at these 2 different ways of representing it as a condensed structural formula, you should see that as you sort of walk down the pentane molecule, you've got a CH3 group, and then you've got a CH2 group, CH2, CH2, and CH3. So that's, you'll often think about carbon chains as sort of these little bits put together. And so if you look at the condensed structural formula down here, that's how it's written: CH3, CH2, 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 CH3. So it's a bit more helpful than just seeing C5H12. It tells you exactly the groupings that piece together. And then an even more shorthand way to write the same thing is CH3, CH2 in parentheses times 3, which implies that you have 3 of them in a row, 1, 2, 3, and then another CH3 group at the end. You can do the same thing for butanone, CH3, CH2, CO, and CH3. So that's the way that you would represent it here as a condensed structural formula. It can be a little bit confusing. You might think that this oxygen has to go between these 2 carbons, but if you actually try to draw that out, you would see that it wouldn't be able to obey the octet rule if you did that. If you have CH3 here, that carbon's okay with 4 bonds, CH2 to this carbon, and then you have this oxygen, which in organic we know is only going to form 2 bonds. So if you try to put it in the middle of a chain, it would look like this. There's the CH3, here's the C, here's the O, and this this carbon here only has 2 bonds to it. And I can't really give any extra bonds anywhere, because if I put an extra bond here, that's going to give this carbon 5 bonds, which I'm not allowed to do. If I put an extra bond here, that's going to give the oxygen 3 bonds, which is not what it's going to do in organic. So this is just not the structure. Even though I'm trying to follow the structural formula, that's not going to work. So there are examples where oxygen goes between carbons, but there need to be some additional H atoms there. So this is not that structure. And so in time, with practice, you would be able to figure out that this oxygen, although it's written to the right, is actually this carbon to oxygen here that's off to the side of the chain. The final type of formula is the most abbreviated, and you won't be asked to draw this on the IB exam. In fact, you're not allowed to use it on the IB exam, but you will see some sort of modified versions of it in some of the bigger structures, and you could be asked to sort of interpret what it means. So in a skeletal structural formula, it's super streamlined. And so whenever you see a line segment, the system is that at the end of every line segment, unless something else is written, there's a carbon. So that line segment has 2 carbons at either end. And there's a carbon at that junction, and there's a carbon there, and there's a carbon there. So there's the 5 carbons of pentane. Now, you may notice there's also no hydrogen. So unless something else is written, you know that every carbon makes 4 bonds, and so you add hydrogen until each carbon has 4 bonds. And so that would end up, I'm not writing them in just because it would be too messy with this little marker, but it'd be CH3, CH2, 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 CH3. And so it would be exactly the same as the formula right here. Again, you're really not going to be asked to look at this very often, except in a couple of larger molecules that they could give to you, but in general, you don't have to deal with this. This is what it would look like for butanone. Okay, so we're going to start our look at organic chemistry just by focusing on the alkanes. There are lots of different families of organic compounds. They each have their own special sort of general formula and their own specific functional group that distinguishes them from other families of compounds. A functional group is an atom or a group of atoms or a specific kind of bond that characterizes that family and has sort of its own specific properties. So things like carbon-to-carbon double bonds, O to H groups, COOH groups, these are different examples of what we're going to call functional groups, and they make compounds belong to different families. So the simplest class of organic compounds are the alkanes. They have no functional group, so they are only C and H single bonded to each other. The general formula for all alkanes is CnH2n plus 2. So if that means if n is 1, just to show you how the formula works, so that would mean that there's 1 carbon, because n is 1, and then the number of hydrogens is 2 times 1, that's 2, plus 2, so 4. So the first member of the alkane homologous series is CH4. Okay, so that's just how you follow that formula. If you plug in a 2 instead, you get C2H6, C3H8. So it's a way of figuring out the molecular formula very quickly. And as the name suggests, ane, the alkanes, whenever you name one of these things, it's always going to end in an ane for the ending. It's suffix. So some properties to know about alkanes: because they're only made of carbon and hydrogen, or they're completely hydrocarbon, they are completely nonpolar. So their only intermolecular force is going to be London forces. They generally have low reactivity because the C to C and C to H bonds are relatively strong bonds. One of the few reactions that they do undergo is combustion, producing carbon dioxide and H2O. The reason they undergo this reaction is that although the C to C and C to H bonds are pretty strong, the C to O double bonds and the O to H bonds that form are even stronger. And so we end up with very exothermic reactions when you have alkanes combusting, turning into CO2 and water. So the fact that they're more or less stable, but they will readily burn and release a lot of heat because they start off totally unoxidized, and when they combust, they tend to, well, they can be fully oxidized. They have very large enthalpy change values of combustion, and they're just really useful as fuels. There's another reaction that we're going to learn that's called free radical substitution. It's one of the only other reactions that alkanes will undergo. And so this term homologous series, it's sort of another term for class or family. It does have sort of a lengthy definition. It's a series of compounds where each successive member differs by one CH2 group. And the compounds have similar chemical properties and show trends in their physical properties as their carbon chain gets longer. So for the alkanes, these are the first 6 members of its homologous series: methane, ethane, propane, butane, pentane, and hexane. So you can see all that's happening. If you count, we're getting 1 more C and 2 more H's each time, sort of like 1 extra link in the carbon chain. So all that's happening is the carbon chain is getting one longer. You may notice that in terms of a name, we have some new little root names to learn that stand in for different numbers. Some of these you've heard of before. The pent and the hex are pretty obvious. Pent means 5 and hex means 6. There are some new ones to learn for 1, 2, 3, and 4 carbons in the main chain: meth, eth, prop, and bute. I will give you a mnemonic in class to try to help you remember that. And then the ending of the name goes along with whatever family it belongs to. So in this case, all these compounds only have C and H single bonded to each other, so that means it's an alkane. So I figure out the number of carbons, and that tells me that it should have bute as the start of its name. And then the fact that it's just all these single bonds means it should have ane as the end of its name. 5 carbons means pent, and then no functional group, so ends in ane. So that's how the naming system is going to work, and we'll do a lot of practice with that. The last topic for the video is just to briefly introduce you to isomers, or isomerism. As organic molecules get bigger, there becomes an ever greater variety of possibilities for how they can get put together. And so the different ways that you can connect the atoms, the different structural formulas that you can get from the same molecular formula, are called isomers of one another. It's a lot like the term isotopes, right? So isotopes were atoms that had the same number of protons but different numbers of neutrons. So kind of different versions of the same type of atom, the same type of, or atoms of the same element. So structural isomers are different structural forms that have the same number of each kind of atom. So here's the kind of the smallest example that we can look at. Butane means 4 carbons. If you apply the alkane general formula, 2n plus 2, you get that there must be 10 hydrogens. The empirical formula would therefore be C2H5. Now, if you play around with the atoms, there's actually 2 different ways to put together C4H10. You can do the simple kind that has 4 carbons in a row and all the hydrogens on the outside. But you can also have 3 carbons in a row and then 1 carbon sticking off of that middle carbon. So this is sort of would be called a branch or a side chain. If you count, there are still 12 hydrogens and 10 hydrogens and 4 carbon atoms. And so both of these molecules have the same molecular formula, yet they have different structures. And so these are 2 structural isomers, or isomers of one another. So we would actually say they're both isomers of butane, because that's what their original molecular formula is. So some people get confused and they think that this one on the right is not an isomer of butane because when we name it, it's not going to have butane in the name anymore, because its longest continuous chain is only 3 carbon atoms long. So we're going to call it propane. And so people get confused by that, but you have to base it on what is the molecular formula. So these 2 compounds both have 4 carbons and 10 hydrogens, and therefore they are called isomers of butane. There's another slightly more spatial representation that looks like our molymod models. The condensed structural formulas would be a little bit different from each other. So CH3, CH2, CH2, CH3. And the one on the right, we'd have something slightly different. So we'd have CH3, CH, right? If you look at that structure. Now, I have to somehow represent that there's something off to the side, a branch. So in parentheses, I can put those branches. So this CH3 group right here represents this CH3 group that's off to the side. And then I can put CH3 here. That's one way to represent it. There are others that we can talk about in class, but that's sort of the simplest way to do it. And finally, the names. So the one on the left is just going to be called butane because it's a straight chain, it's got 4 carbons in it, and it's an alkane. The one on the right, the longest chain is 3 carbons long, which in organic chemistry is prop. There's no functional group, so it's going to be propane, but I still have to tell you that this other group is here. And as we talked about in the previous slide, the word for one carbon is meth. And so when I name this thing, any sort of side chains get named in front of the parent name. So the main chain of this molecule is propane, but in front of it is a meth, sort of like a meth group. So the way that we name that in organic chemistry is we call it a methyl group. So this is propane with a methyl group off of it. So the full name is methyl propane. And notice if you add up meth meaning 1 and prop meaning 3, you get the same 4 carbons that you do out of this but word. So both of them have 4 carbons, just one of them has them in a continuous chain, and one has a chain of 3 with a chain off its middle carbon. So we'll look at more compounds, more isomers, and more names when we get to class.